forgot to pin myself. I think it's too early in the morning. Okay, so what are we going to do with this circuit? What are we going to measure? And really what we want to do is look at the current rule and the Kirchhoff's current rule and the loop rule. So what we want to look at is, for example, is the current here that splits up at this junction, is this current equal to that plus that? Is this current here equal to this current plus that current? Now you would think, oh, I got to measure current in this lab. Well, for this measurement, you only need to measure one current directly. Okay, and the reason why is because you're going to be wiring the circuit on this board. This is the circuit I've wired up. And it's really hard to put the multimeter here, 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 and here. So you might be thinking, okay, how am I going to get this current, this current, this current, and this current? We're going to get them indirectly. So the first step, measure R1, R2, R3, and R4. Actually, before you put them in the circuit, measure their values. Don't go with the color code. Then you put the circuit together. Measure I sub S, which is this. So what you'll do is you'll put the ammeter here and measure I sub S. Now, I'm going to leave it up to you as to whether or not you want to leave that meter there the rest of the experiment, at least in part one. Okay, I'll leave it up to you. If you want to take it out, then go for it. So let me tell you the advantages and disadvantages of leaving that in. If you leave that in the whole time, you always run the risk of maybe blowing a fuse. Okay, so if you leave it in the whole time, you run the risk of blowing the fuse. Well, what if you take it out? What would be a problem just taking it out? What do you think? It has to do with your data. Yeah, the resistance of the multimeter, because if you take it out, then you're changing the resistance of the circuit. Now, granted, the resistance of the multimeter probably isn't going to be that high. Okay. It might be a few ohms, and it's probably going to be small compared to the rest of the circuit, so you won't notice a big error. But when you calculate, when you compare this current to the sum of these currents, you will see a difference. It'll be a small difference, and then that'll give you the systematic error. But you know what the systematic error is because you took that out, right? Because if you make the measurement with this in there, then when you take it out, you're going to have that systematic error. On the other hand, if you leave that in the whole time, you run the risk of blowing a fuse. Which multimeter should you use? The small one or the big one? I would use the big one. And the reason why is because it's more accurate. I'll talk about that a little bit later. Okay. So once you've measured I sub S, then you measure VR1, VR2, VR3, and these should be deltas, sorry. So all these are the things that you're going to measure. Okay, and it goes fast. Okay, it goes fast. Oh, I forgot one more thing. I'll put it here. Measure. And this one, it doesn't matter where you do it, but the power supply voltage. Right. It says to set it to 6 volts, but it won't be 6 volts. So those are all the things you're going to be measuring for this circuit. And it actually doesn't take long, because all you got to do is take the multimeter, put it here, 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 and here. So it doesn't take long to do those measurements. Okay, this one's going to be a little bit of a pain because you actually have to put it into the circuit. Okay. So then what? Well, then you can calculate I1, I2, I3, and I4, along with their uncertainties. I'll talk about the uncertainties. So you got to calculate this along with delta I1, delta I2, delta I3, and delta I4. How am I going to calculate this? Anybody want to guess as to how I'm going to calculate I1 if I know this and that? You use Ohm's law. All right, you're going to use Ohm's law to calculate this. And then you're going to use air propagation to get all these. Are we okay so far? Then you're going to calculate I1 plus I3. In other words, is that equal to I sub s? Then you're going to calculate I2 plus I4. Is that equal to I sub s? And of course, you're still going to do air propagation on here. Okay, you still got to do your air propagation. Okay? So the data is easy to collect, right? You move the multimeter here, 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 and on the meter, and then measure I sub s, and then measure these guys. All of those take very little time. What's going to take you the most time is building the circuit. What do you mean, where are the other currents? Well, obviously these two currents should be the same, but I'm calling them IR3 and IR4. I'm sorry, IR1 and IR2. IR1 and IR2 these currents should be the same. Okay. And then, of course, these two should be the same because they're in series, right? Okay, so along with all these are uncertainties, and I got to talk about that later. And so really that's it. And then there's some questions. Okay, now one of the questions has you verify the loop rule. You pick a loop that you like, whatever loop makes you happy, and you show that the sum of the voltage drops equals 0. And calculate the uncertainty in that. Okay? Because you want to see if the sum and your uncertainty overlap the value 0. Then you know you've verified Kirchhoff's loop rule. Okay? So you'll answer the questions, and that's it for part 1. Yeah, this is one of them. Right? I mean, there's a lot of air propagation in this lab. Because you have to do it in calculating this one's easy to do. This uncertainty is easy to calculate. In fact, this uncertainty is actually easy to calculate too. All of them, all the equations are pretty easy. So you want to show your work. I don't want you to show me your air propagation calculation for all 4 of these. Show me one. I don't want you to show me the air propagation for both of these. Just show me one of them. Because if you know how to do this one, it's the same equation. You should be able to do the other one. Okay? Yeah, you have to, right? It even says in the problem, calculate your uncertainties. Right, because that's what I said. I said you want to see that your value, your sum of the voltages in the loop is some number plus or minus an uncertainty. You want to make sure that that overlaps 0. Okay. So this is one of 3 labs where you're going to do some heavy duty air propagation. This is probably the most intense one of the semester. Okay. So this is part 1. Now what about part 2? Okay. Same circuit. But this time we're going to put a multimeter between these 2 points. We're going to measure current. This is not going to be a balanced circuit. I purposely chose the resistor value so it's not balanced. So there's going to be a current going through here. And so when you get to this point, some of the current will go this way. I'll call this I1, I3, I2, I4, and I'll call this IAC because this is point A and this is point C in the diagram. Again, you're going to make these measurements, okay? You're going to make the same measurements. You're also going to measure this. So for this part, and listen carefully, this will be here during the entire measurement. Keep it here, because if you take it off, you completely change the circuit. This has to be here the entire time. Okay? Why does this change the circuit? Because ideally the ammeter has no resistance. So basically you're tying these 2 points together when you put the ammeter there. So that always has to be there. As opposed to this guy, it's in series with the rest of the circuit. So whether you put it in or take it out, if it's an ideal ammeter, it ain't going to make a difference. So this has to be there the whole time. Okay. So for part 2, in fact, for part 2, you're going to make these measurements twice. And so you're going to measure IAC. Oh, not, sorry. Use a small multimeter for IAC. Okay, so for part 2, small multimeter. At the largest current setting. That gives you a measurable value. Why do I want you to use their large current setting when you're measuring that? Anybody want to guess? Why do you want to use the largest current setting? Well, is this ideal? Is this ammeter ideal? No. So it does have resistance in it, right? When you run it at a higher current setting, its resistance is the lowest. The higher the current setting, the lower the resistance. And so what I'm trying to get you to do is to minimize the resistance of the meter. Okay? And so you're going to do all these measurements with this thing here the entire time. This one you're going to have to take out because you're going to have to use it to measure the voltages. Okay? So you have to take this out of the, because you only have 2 multimeters. If you had 3, that would be different. Okay? So in part 2, you don't have a choice. You have to take this out. You measure I sub s and then take it out. Is everyone clear on that? In part 1, that's a good question in part 1. You want it at the highest setting. There's a trade-off between sig figs. There's a trade-off between sig figs and then you're adding the systematic error. The higher the current setting, the less sig figs you get. And it turns out the less accuracy. So, and we'll talk about that a little bit more because you're going to need to use the manuals that come with these meters. So you don't want to use the highest setting because for I sub s, you could probably go on a 10 amp scale, but you're going to get like 1 sig fig. Okay. I forget what the resistance is at the 20 milliamp scale. I don't remember, and I don't know if you can go that far down. What you can do is compare the results on the 20 milliamp scale, the 200 milliamp scale, and you can try to. I wouldn't try the 10 amp scale because the current's going to be too low. Okay, Chase? You can compare between the 20 and the 200 milliamp scale. Okay, so you're actually in part 2, you're going to do this twice. So you do these measurements and then you're going to do them again where the small multimeter is at the smallest current setting that doesn't blow the fuse. So this data is table 2. This data is table 3. You're going to do the same calculations, except that you're also going to calculate IAC. Which is going to be this minus the... Did I number my resistors incorrectly? Hold on a second. Yes, I did. Sorry. I switched those around. Okay, so IAC is going to be this current is going to be this minus this. Okay, and again, you're going to do the air propagation for everything. So the question is, how do I figure out my uncertainties? How do I know what my uncertainty is in the measured value of R? Your multimeters come with a manual. It's not a long manual, it's a very short manual. Okay, so when you measure, let's say when you measure current, or let's say when you measure resistance, let's say the manuals say your resistance accuracy is 1% plus or minus 5 digits. What the heck does that mean? Okay, that's your accuracy. So this is not the uncertainty due to precision. This is the uncertainty due to precision and systematic errors. The engineer, when the engineer designed it, they know how to take into account the systematic errors. So this is your actual accuracy. It takes account of everything. Of course, you can, as you're doing in the experiment, you can still have other systematic errors, like having I sub s in there, okay, but still. So how do I determine my uncertainty in the resistance? Let's assume, let's let I be, R equal 250 ohms. I want delta R. First of all, what the heck does this thing mean? This tells you the accuracy of the last digit. This tells you the accuracy of the least significant figure. Actually, let me do this. Let me make it like that, okay? This tells you the accuracy of this one, okay? If this was a 1, then the accuracy would be 0.1. If this is a 5, the accuracy would be 0.5. Okay, so this tells you the accuracy of the least significant figure. Okay, this tells you the accuracy of the least significant figure. So I know my uncertainty is going to be 0.5, but it's also going to be 250 0.1 times 0.01 so 2.5 plus 0.5 is 3, so delta R. So then I would report my measurement as 2.50 plus or minus 0.03 times 10 to the third. Questions on that?
I have a question.
Yeah.
I was searching about this on the internet, and they said that if you have plus or minus 5 digits, it is like saying that you can add or subtract 5 from the least significant figure.
Correct.
So can the value be like 250.6 and then subtract 0.5 from it as well? Like, does that give a range of values then?
Yeah, it does, right? That's why you have the plus or minus here, right?
Yeah, but then what is with the 0.5 on the left?
This one?
Yes, did you add it to the original value
Yeah,
at
I
the
added, well, I added this to that. This is the 1% uncertainty, and I added it to the 0.5.
Could we subtract it as well?
Yeah, but then you're probably underestimating the error, right?
Okay, so we want the highest error.
Right. I mean, don't you want to be on the safe side, right?
Yes.
Okay. So you do want to be on the safe side
Okay.
because this is an additive value. Yeah, you don't always you don't want to make it look positive. You always want to be, as an engineer, you always want to be on the safe side. Okay, or as a scientist. Other questions on this? So for all your measurements, you're going to have to figure that out, and so you're going to enter these uncertainties, the uncertainties in this guy, the uncertainty in this guy, in the tables. Okay. Now this is the only one you're going to really calculate. I don't need to see the work for you calculating these. I want to see the work for these ones.
Can you shift your camera?
I'm sorry?
Can you shift your camera to the right?
Oh, sorry. That's weird. The camera just changed. Okay. So, Kathleen, so I took 250.1, multiplied by 1%, that gave me 2.5. Then I added to the half digit, gave me 3. Okay, so this is always the uncertainty in the least significant figure. And realistically, if you this number probably will not always play a role. Okay, because this number is always going to be bigger. Okay. Actually, you know what? I think I made a mistake. Oh, no, we're okay. Never mind, we're okay. Yeah, so this number will always be at this decimal place. So it might not always play a role because I always got to round up. Because if it was like, and I added 0.5 to it, then you know I got to use the rules. I got to round off here. Round off to the nearest even. So in this particular case, it made a difference, but it doesn't always make a difference. Because I got to report this thing to one digit, right? So this term doesn't always make a difference. Now, if you look at your manual, you will find for measuring currents, the bigger meter is more accurate on certain scales. Okay? So you have to read the manuals, okay, for this lab. So this is the one for the little meter, if I remember correctly. No, this is the one for the, this is the one for the little meter. This is the one for the big meter. Okay, they're not very long manuals. They're not very well written, but the tables are easy to read. Are there any other questions regarding the lab?
I have a question.
Okay.
So generally when we have like two paths for current, we say that it would go in both, right? When they have resistances,
Yes.
although they can be different. But then if you don't have resistance in one path and only in the other, it would only go in the one with zero resistance, right? Or almost zero resistance.
Yes, ideally. We're assuming the wire is ideal, yes. So if there was no resistance here, the current will go this way.
So when we measure the current with an ammeter, can we say that the current does not pass through R3? because the ammeter gives it an almost zero resistance path. Like, I don't know how to.
Oh, so you're talking about this point, this one right here. You're
Yes.
saying all the current should go this way.
Yeah, I'm not sure whether it would do that.
But then you have this current too, right?
Yes.
So yeah, I think well because of that, that's not going to happen. Imagine they're going to be competing against each other, right?
But then wouldn't all the current go through R4 then if that is the case? Like both the currents add up at that junction and they go to R4.
No, why would they do that?
Current can be only in one direction, right? Like in one wire.
Well, but it has a choice ahead of time, right?
Yes.
Okay, so why does it have to be? Why does it all have to go this way when this one can take? When this current could keep all of it from going this way?
Would it also depend on the resistances R1 and R2, which is the lower one?
Yeah, it's going to depend on these resistances. That's true. But
So
it's not all going to go this way. This is not going to be bypassed in this particular case.
Mm-hmm.
I mean, just imagine water flowing through a pipe, right?
Mm-hmm.
Right? If there's nothing that would keep, I mean, you got to consider water going this way and then water coming this way. This water is going to make it harder for this to go by. Isn't that true?
Yes.
Okay, so you can't have all of it go through.
Mm-hmm. Therefore, it has to pass through R3 as well?
Yes.
Okay. Yeah, these are like, sometimes when I think about it, it gets confusing sometimes.
Yeah. Other questions? I want to show you the circuit that I built. You don't have to build it the same way, okay? Tyler does not have a video on YouTube for this because I think this is a more straightforward lab. Okay, so, hold on a second, let me change. I'm going to be holding it in my hand. Oops. I'll put it in front. So this is the circuit, R1, R3, R2, and R4. This is my power supply. You don't have to hook it up this way, by the way, okay? Can you all see that okay?
Yes.
What's the red, what's the orange and the white wire for? Yeah, the ammeter, that's between points A and C. Okay? Now in part one, you don't need these two, right? Part one, you can pull those out. And then for measuring isobs, all you need to do, you see this red one and this, this yellow one and this red one? I would put the ammeter between those 2 points. Oops, sorry, I can't see it. So you pull this one out and you pull this one out. I'm sorry, not that one. You go between these two, sorry. Or you go between these two. Okay, to measure isobs. So you can use these two wires for isobs. You put the meter in between these 2 points. Okay. Questions on the circuit? Let me rotate it so maybe you can see it better. I'm leaving it here so that you have something to look at when you're building the circuit. It doesn't have to be this way. I could actually make it a little bit easier than this. Because I can actually connect this point to this point directly, this point to this point directly. We okay with this one? Okay, so I'm going to take it away so I have to hold it up the whole time. All right, so I didn't, in class on Tuesday, I went through very quickly this device, this thing called an oscilloscope. And what it does is it plots voltage on the horizontal axis. I'm sorry, time on the horizontal axis and voltage on the vertical axis. And you're going to learn how to use these after spring break. Okay, so the rest of your labs, after the DC circuit analysis, you're going to be using this device along with the multimeters. Okay, and it's this device that's very important to learn how to use because of the fact that this thing shows you everything you need to know about a signal. The multimeter doesn't show you much because a multimeter just gives you static values. This gives you a more dynamic value. In other words, you can see things changing with time with this thing. Okay, so you have one of these in your kit, and over the break, if you have time, you can play around with it. Okay. Questions? The questions before the exam then? Because I can use the time now to answer questions before the exam. Was there a homework problem that caused grief?
I have a question.
Okay.
It is just a conceptual question. Like when you have a capacitor connected to a battery and it is fully charged, when you try to increase the separation in the plates, then the battery does negative work on it.
Well, let's see, if you increase the plate separation, the battery puts more charge on the plates, correct?
It puts more charge?
Oh no, wait. You said you're increasing, so you're decreasing the capacitance, right?
Yes.
You're decreasing the capacitance, and the energy stored decreases. Yeah, so it does negative work. You're correct.
Okay, so but we are doing positive work on it.
Yes. Because the plates attract each other, right?
Yes.
Okay.
So because there is an overall decrease in the energy of the capacitor, so that means that battery is doing more work on it than we are.
Correct.
So I was not able to see how the battery is doing more work than us.
What do you mean?
Like I can tell that it is doing negative work and we are doing positive work, but then how to compare the two values?
Yeah, that's very difficult because you have too many unknowns, right?
Mm-hmm.
Let me think about that. Because you can only calculate the overall effect. You would have to calculate the force on the plates, right? And then from that, you'd have to calculate the work that you do on the plates as you increase the separation.
Mm-hmm.
Then you can look at the work done by the battery. Does that make sense?
Mm-hmm. Yeah.
Okay. So it's not an easy calculation.
Okay.
But I mean, it can be done. So you would have to figure out the force on the plates, and then Well, first you're gonna. I'm assuming you're gonna increase the separation of the plates at a constant speed, so that you're applying an equal and opposite force on the plates to increase the plate separation. And then the work done by that, you calculate the work done by that, and you know your final energy of the capacity system. Then you can calculate the work done by the battery.
Okay.
Yeah, that takes a little bit of doing.
I have a question.
Sure.
Number 12. You don't have to do the whole problem, but I was confused on the setup.
Okay.
Like, I was thinking of doing like 3 inner loops, but I don't know if there's a better way to do it, or if that's even correct.
So we want to find the current, the current in the battery V1. Okay, so let me draw a picture. Let me erase all this though.
Can you change your mic?
Oh yes, sure. I will unplug this. Yeah, if I had normally I would add more USB ports. I would buy a hub, but my computer is just using too many resources. Okay. So okay, let me copy this down. How many loops do you think you need, I guess?
What number are you doing?
This is number 12, right? Oh, no. Oh, I'm sorry. I'm sorry. I copied the wrong picture. Okay. That's what I would do. What did I do? What did I do to the picture?
You combine the resistors in parallel.
Yeah, so I would combine those two right away. Okay.
Doesn't that like suggest that there's different currents running through the bottom?
Yeah,
You
I
know,
mean, I took that bottom wire, squished it down to nothing, but that's okay. I mean, we can get to that later. I know the potential across the 4R resistor and the 3R resistor are the same, right?
yeah.
Okay, so we'll deal with that bottom wire that I got rid of later. I can still calculate, it's not going to make a difference. I can still calculate this current, and this current. And I gotta be careful with my labeling. I will call this I2, I will call this I1, and this is I1 plus I2. So what I'm going to do is set up the loops. I have two loops, one here and one here, and then I will solve for this current. Once I solve for that current, I multiply by this resistance, and that gives me the voltage across each two of those resistors, correct?
Yeah.
And so if I know the voltage across each two of the resistors, I divide by the resistance, and that gives me the current through each one of them. And then I use the current rule. So now let me draw this figure with both resistors. So the voltage across this one is going to be that's the voltage. Okay, so then the current is that. Of course, you still got to figure out I2 from there. And then this one so I know this current, and I can figure out this current, right? Then I can use the current rule to figure out what that current is. I might have one of these backwards, but just be aware of that. Okay. So then this is going to be this plus that. Does that make sense? These 2 points are at the same potential, whatever they are. You can call them 0 if you want, Ravtesh. It all depends on what this is referenced to. Yeah, usually I reference it to 0. Is that enough for that problem, or?
So I was confused on like what I get how you got the I4R and I3R, but I've missed the overall like.
Okay. It's just that you gotta go through the work to figure this out, right?
Yeah, I know.
Okay. But that's
I just mean like, what do you? I missed. What do you do with the I4R and I3R again? What do you do with those?
well, you either if you know this and you know this, you can calculate this, right?
Yeah.
Okay, because you can calculate this from the loop rule. That's this current. Or
Yeah, I see now.
if you know this current and this current, you can calculate this current. So you can either go on this side or that side and get it.
Okay, I got it.
Okay. And now the hard way, you can do it the hard way, right? You can do 1, 2, 3 loops and do it that way, but that's more work. I mean, conceivably, you can call this the sum of this current, this current, this current, and then do 3 loops. It's just more, I think it's more, it's easier to make a mistake when you have extra loops. And if you take circuits, You will learn techniques to make this thing really simple. Is that okay then?
Yes.
Other questions? No other questions? Y'all went through the practice test? Okay, so the only thing you have to worry about over the break is this. So hopefully, you can enjoy your break. I'm not sure what your other classes are like, but when we come back after the break, your lab will be a project. You're going to build a motor. Okay, and that's in your kit. So usually that's a fun project, although it's a little bit different when we're online. When we're in person, it's a little bit more fun because you have more tools to test your motor with in the lab. When you're doing it at home, it's a little more difficult to test your motor. So I'm going to treat it more like a project, the motor, and basically you're going to build a motor that works at a certain voltage. Your goal is to make the motor work with only 3 volts, and then you get a very high score. Okay. And the motor should be, we give you the instructions to build a motor, and we give you the kit. It's just a matter of making it work efficiently. Anything else?
I have a question.
Sure.
So on the last question, which was on the practice exam, like it was like an anode which is square shaped and it has a resistive coating on it.
Yeah.
So for that, when you move, like if you have a point on the anode, suppose it is in the first quadrant, and then when you move towards the x-axis, the potential is increasing and then it starts decreasing because both the borders are equipotential.
Okay, let me draw the picture. So this is your resistive anode.
Yes.
Okay, let me draw. So my coordinate system I chose was this.
Mm-hmm.
So you're talking about you're at this point, and so what you do is you measure the current here. You have an ammeter here. You have an ammeter here, and you have an ammeter here, and another ammeter here. And so you collect the current depending on where this goes. So you're saying as you're going towards the x-axis?
Yes.
So as you go towards the x-axis, then this resistance increases. Right? The resistance from here to here increases. So this current decreases. And this current increases.
So I was just thinking about the potential difference because they said that the borders are equipotential, so delta V would be 0 between the 2 borders. And if there is some potential in between, like if the point is in the first quadrant, when it moves towards the other surface, the potential would increase till the x-axis and then decrease.
Well, the delta V is going to be the same here and here, no matter where you're at. I mean, delta V will change, but this delta V and this delta V have to be the same.
Because they're equipotential?
Yeah, because let's say this is at 0 volts and this is at 0 volts, this is at 1 volt.
Mm-hmm.
So this difference and this difference is still the same.
Mm-hmm. Okay. So when you measure the current, suppose through the ammeter on the top, the distance would be um, whatever that is. I think it was L over 2, and then you subtract of Y.
Yeah, the resistance is due to L over 2 minus Y. That's right.
Okay. Because sometimes I can think like, because current is in the direction opposite to in which electrons move, right?
Correct.
So if the electron is moving in the other direction and we are measuring current in the opposite direction, could it be the case that the distance for the ammeter on the top is actually the distance L over 2 plus Y?
Well, the electrons are going this way, right?
Yes.
Okay, but we're talking about the resistance. The resistance depends on this length.
Yeah, it depends on the length that the electron travels, right?
Or the positive charge. So
Yeah,
either the electron
either.
is going from here to here, or positive charge goes from here to here.
So isn't the electron going from that point and then towards the edges? Because that is where it dropped, right?
Oh, you mean the electron that hits?
Yes.
Oh, okay. I mean, it's going to either go this way or that way, right?
Mm-hmm.
But I'm not sure I'm not sure about your question.
So, like, if I just simply look at it, I can tell that, okay, the distance would be L over 2 minus Y for the top ammeter. But then I think that the current is usually measured in the direction opposite to where the electron travels. So if the electron is actually traveling in the negative Y direction, so the current would be measured in the positive Y.
So you're saying that this current represents the electrons going that way.
Yeah, I was thinking about that.
Let me think about that. All right, let me think about that, okay?
Okay.
Okay. Other questions? So I'll give you an answer, Raftesh, on that one.
All right.
Okay, I'll try to email you. Nobody has any other questions? I guess so I'm going to end it early then, okay? All right. I'm going to end it early. And then I'll see you folks at 2. And also have a good break.
Thank you.